Let me give Alberto one more shot, see if there's some magic here. No, it only gives me to remove permission. So it says I've given it to you. So I don't know what's going on there. Okay, let me fire up OneNote here. All right. So okay, so I'm assuming everyone can see my OneNote. Let me know if that's not the case. And let me see if I can recover where we were. Well, I'm not sure. I think I'll just start fresh instead of punting around. So let me just go down to the okay, that looks like it's working. So let me start by reviewing some notions and then going on from there. So last time we talked about linearly independent and dependent vectors. And key notions were on page 37 and 38. I'm opening the book. So page 30. So on page 37, there's this important definition. It says a subset S of a vector space is called linearly dependent. So I'll sort of give it in short order. A subspace, a subset of a vector space. This is a vector space. So given that, S is called linearly dependent. If there exists a finite number of distinct vectors, yes, a finite number of distinct vectors U1, U2, all the way up to UN. In S, and scalars A1, A2, all the way up to AN. So these are scalars, they're in the field. I guess I could say that AI would be in the field, usually the reals from what we've been doing, such that and the key thing I left off, the constants have to be not all zeros. So these have to be not all 0, such that what? U1, U1, that's A2, U2, all the way up to AN, UN, 0 vector. So we're defining what we're talking about linearly dependent. If we can find a finite number of distinct vectors, U1 up to UN, distinct means these are not the same, and scalars, same number of them, 1 through n, not all 0, that's key. And these are in the field such that this linear combination equals 0. Now, if you can find that, then the fact that, so let me just say underneath what this definition means. So this is definition on page 37. Definition of what it means to be linearly dependent. And probably here's the afterthought or some note. If, for example, A2 was the coefficient that was not 0. Now be careful. This is the 0. This is the 0 number in the field. This is the 0 vector. So there's always that confusion here. But suppose A2 is not 0, then what can you do? You could write A2, U2. You can bring all these other vectors to the other side. For instance, A1, U1, A3, U3, etc. A4, U4. So you get your way down to the end, AN, UN. And if you want, since A2 is not 0, you can divide everything through by A2. On this side, when you divide by A2, you'll just get U2. And on the right side, what would you get? You would have that minus A1 over A2, U1, minus A3 over U2, U3, minus A4 over A2, U4, all the way down the line until you got to minus AN, UN over A2, which means what? This vector can be achieved in terms of the other vectors. And this is why it's called linearly dependent, because you can create this vector from the other ones. And you can do this because A2 is not 0, so you can divide both sides, and you actually get U2 to be a linear combination of the remaining vectors. So that's the nice thing about this definition. Okay. The other side of it is on the following page. On the following page, well, before I even go to the following page, any questions about this definition, because it is important?
So do we say that the vectors are linearly dependent or that the space S is?
Well, it's actually, you could say both, but this is saying this, the subset. Remember, S is not necessarily a space, be careful there.
Right, subset.
It is a subset. If there are vectors like this and scalars like this, where these aren't all 0, then you would say the set S is linearly dependent. But you could also say that these vectors are linearly dependent. So you can actually use that phrase for either. Any other questions? Good question, though. Okay. Now, if we turn the page, look at page 38, it has a definition of linearly independent. And so I'll just quickly write that definition, not two definitions. S, a subset of a vector space. So S, subset of a vector space. So it's the same setting as above, so I won't repeat it, at least not, I repeat it, but I won't write it out, is called linearly independent. That's not the same as above. It sort of should be the opposite, right? It's called linearly independent if it's not linearly dependent. But let me write it in a slightly different way. It's called linearly independent if whenever you still have those same vectors, u1, u2, up to un, they're still distinct. So they have all the properties of the first definition. And you're looking at this linear combination, and a1u1 plus a2u2 all the way up to an un equals 0 holds only if a1 is 0, a2 is 0, a3 is 0, if they're all 0. Well, it's pretty clear if all the a's are 0, this will hold, but it's the only part. There's no way for this to hold when one or more of the a's is non-zero. So the only way this linear combination could be 0 is if all of the a's have to be 0, which is the opposite of what we define to be linearly dependent. Then we call these vectors or the set linearly independent. And actually, well, we've done an example or two, but we could look at example 3 right after this. So let's just look at that. Example 3 from the book. Well, they give this example. They give the set S to be 4 vectors, 1, 0, 0, negative 1, 1, 0, 0, negative 1, and 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 0, 1, negative 1, 0, 0, 1, negative 1, and 0, 0, 0, 1. So this would be a subset of what we would call R4. Those would be vectors that have 4 components. Let's make sure I wrote this correctly. This example is on page 38 at the bottom. And they say to prove, they want to prove that this set is linearly independent. And at the bottom, they say we must show that the only linear combination that equals 0 is the one in which all coefficients are 0. So what we need to argue is if, so to show S is linearly independent, we need to show if there's only 4 vectors in here. So if we took A1 times the first one plus A2 times the other one. Plus A3 times the third vector. Plus A4 times the last one. Set this linear combination equal to the zero vector, we need to show if this is true, the only solution is A1 equaling 0, A2 equaling 0, 3 equaling 0, and A4 equaling 0. Now, it's not as easy maybe as R2 and R3 would be. You can see that the vectors in those places, it might be easier to see whether the vectors can, if you could form a linear combination where you can get one vector from the other. If you can do that, then they're linearly dependent. We're saying that that can't happen because we're saying the only way this linear combination can be zero is for all of these coefficients to be zero, which means you won't be able to do the little trick we did up here where we can solve for one vector in terms of the others. Why won't you be able to do that? Because you can't divide by the a's. The a's have to be zero. So you won't be able to get one vector in terms of another. Okay, so how do you actually show that this collection is independent? You need to show that this is the only solution. And what they do, it's pretty straightforward. So let's just redo it. Let's equate components. Now this is the zero vector, so I'm going to write that just to make it even clearer, I hope. I'm going to write this zero vector as what? 0, 0, 0, 0. Why? Because now I'm saying that if this equation held, then what I can say is the first components would have to be the same on both sides of the equation. This one has a first component of A1. There's no first component here because you have 0. There's no first component here because you have 0. There's no first component here times 0 because anything times 0 is 0. So this would mean that A1 has to be 0. Well, that's a good start if we're trying to show this is the only solution. So far, by comparing first components, we've shown that A1 has to be 0. Let's compare second components. There's no, the second component here will be 0 because A1 times 0 is 0, but the second component here will be A2. Second component here will be 0. Second component here will be 0. Second component here is 0. So what do we get? We get A2 is 0. So we're sort of half done. We're trying to show the only solution is all zeros, and so far we have 2 of them. This is a nice example. It could be much more complicated than this, but is this clear what I'm doing? Okay, let's finish it off. What would be the third component of the vector that you get on this linear combination? Well, there'd be no contribution from this one because 0 times A1 is gone. A2 times 0 is gone. A3 times 1 is A3. There is no contribution from this, and the third one here is this. So look, you've already got the first 3 have to be 0. So to finish it off, all we have to do is compare the fourth components on both sides of the equation. This would be A1 times -1, so that would be minus A1. This one would be A2 times -1, so that would be minus A2. This would be A3 times -1, so that would be minus A3. This would be A4 times 1, so that would be A4. And what are we comparing it to? It's 0 on the right side. So this time we get something more complicated, but we've already seen that A1 and A2 and A3 are 0. So since these 3 terms are 0, this just reduces to A4B 0. Which means we're done. We've shown that each of the coefficients here, sorry about that. This thing disappeared on me. Minus A1, minus A2, minus A3, plus A4. But anyway, these are 0, so A4 is 0. So we've shown that this set is linearly independent because the only way the linear combination of these four vectors could equal the zero vector is for all the a's to be zero. Questions? Okay. They do another example. Trying to think if it's worth doing the second example. Maybe. Yeah, examples are important, so let's do the second example. Any questions before I flip the page? So on this sheet, we've defined linearly independent and dependent, and we've given an example of a set that's linearly independent. When the set is linearly independent, that's more important for us than when it's linearly dependent. You'll see why soon. Okay, so let me just add to this. You know, okay. Example 4 on page 39. Here, the vector space is this. So this stands for polynomials of degree n in the field F. I'm going to change F to be R just because it's familiar to us and a little more real, no pun intended. Okay, so what do things in here look like? So things in here, polynomials of degree n look like a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a1 x plus a naught, where all of these coefficients, and I guess I should be careful, maybe I don't want to call them a's. Yeah, I probably should call them b's. Bn minus 1 all the way down to b0. They're all real numbers. And this would be an nth degree polynomial. That's a vector space. We've seen it before. They're asking us to look at particular vectors. The particular vectors they're asking us to look at for all have coefficients 1. So P0, so consider the set S that has P0 of X and then P1 of X and P2 of X all the way up to Pn of X. And let me tell you what they are. So P0 of X looks like this. X to the n, let's x to the n minus 1, all the way down to x to the first plus 1. So it's an nth degree polynomial, but each of the coefficients, the b's, are each 1. This is P0. P1 of X looks the same, except it doesn't go all the way down to 1. It goes all the way down to x. So the last term is just x. And it goes on from there. So P2 of x. But all the coefficients are still 1. It just has one less term. So P2 would look like this. But the last term would be what? X squared, and so on. And when you get to, so you can look at the index, it's telling you when you have P1, it's the last term is x to the 1. When you have P0, the last term is x to the 0, which is just 1. When you have 2, the last term is x squared. When you get down to what? Pn, then the last term will be x to the n. So then you just have just x to the n. Okay, so this is the collection of the p's. What are we trying to show? We're trying to show that the collection is linearly independent. So you assume, so we wish to show that this collection S is linearly independent. Okay, this is different than the previous example because the vectors are polynomials of degree n. And they all have coefficients 1, so they're very specific. Okay, so what do we need to show? We need to show if A1, and so you can think of this. Oh, let me think about it. Yeah. So if you have coefficients A0 times P0 of x plus A1 times P1 of x, all the way to the end of the line, the last one would be n, so that'd be an times Pn of x. If this is the 0, now how does the 0 polynomial look? It looks like 0 times x to the n plus 0 times x to the n minus 1, all the way down to all the coefficients are 0. So the last the constant one would also be 0. If you have that, then what we wish to show, need to show A0 equal A1 equal A2, all the way to the end, which is AN, must be equal to 0. If the only way that the linear combination of these polynomials could equal the 0 polynomial is if the coefficients are all 0. Okay, you do the same kind of thing we did in the previous example. If you're looking at, let's see, let's look at the components here. Let's look at the constant term. The constant term, when I've written it in this sort of backward way, let me see if that's okay. Well, I guess, oh no, this is all okay, I guess. But the constant term is only 1 for P0, right? Because all the other ones don't have a constant term at all. So the constant term from this one would be A0 times the constant of P0, which will be the 1. So you'll get A0. All the others do not have a constant term. And the constant term would have to be equal to the constant term on the right, which is 0. So you get immediately that A0 has to be 0. Let me say again how I got that. I'm comparing the coefficients of the powers of x, and the constant term, there's only one of these polynomials that has a constant term, that's P0. So it would be A0 times that 1, that's the component essentially, and that would have to be equal to the 0 on the right side. So that's how that's obtained. What about if we look at the last two terms? Okay, so the last two terms, or what's not even the last two terms, the component would correspond to x to the first. So A0 times P0x would have the component here would give you an A0. And the component for this one would give you an A1. And that's got to be equal to the x to the first component of this, which is also 0. So let's make sure we're all clear on that. There's only two polynomials here that have an x to the first term. P0 does, and P1 does, and all the other ones don't, because you chop off the earlier terms. So it would be A0 times 1 here and A1 times 1 here. And that would have to be equal to the coefficient of the x to the first term over here, which would be 0. So you get this equation. And now you get the idea of how this works. If you're going to look at the component being the coefficient of x squared, P0 has an x squared coefficient, which is 1. P1 has an x squared coefficient which is 1. And P2 is that right here has an x squared coefficient with the coefficient of 1 as well. So what does that mean? When you multiply A0 times the first one, you'll get this, and you get this, and you'll get this. And that would be equal to the coefficient in the 0 polynomial, which would be 0. Well, if you follow what I'm saying, you can see how the equations continue. They will continue in this manner until you get to the coefficient of x to the n. And each of these polynomials have a coefficient of 1 when you're at x to the n. So that's going to give you A0 plus A1. So there's all the ones in between, but I'm at the end now. So if this linear combination equals the 0 polynomial, that would imply that all of these equations hold. But notice, this one gives you that A0 is 0. If A0 is 0, then this one gives you that A1 is 0. And if you know that A0 and A1 are 0, then you know that A2 is 0. And it's sort of just like a stack of dominoes. It all one implies the others. And when you get down to the second to the last one, you already know that all the coefficients up to from A0, A1, A2 up to AN minus 1 are 0. And that will imply what? AN is 0. And that means the only way that this linear combination could equal the 0 polynomial is for all the coefficients to be 0. And that means we're done. We've shown it's linearly independent. Questions on this example? Now, if you were able somehow, if you had other polynomials here, and you were able to get one polynomial as a linear combination of the others, then that would be showing that that collection of polynomials is linearly dependent. Okay. There are two big theorems here. Let's at least talk about what they say. So I'm just going to summarize what they say. Same section, there's theorem 1.6. And what does it say? It's on page 39 underneath the example we just did. It says, let F be a vector space. I'm sorry, let V be a vector space. And suppose you have two subsets. Suppose you have subset 1 contained in subset 2, which is contained in the vector space. So these are subsets of vectors. If S1 is linearly dependent, if this set is linearly dependent, then S2 is linearly. That's it. Okay, proof exercise. The book doesn't even go through the proof because it's somewhat easy. And I'll let you worry about it as well. I can't resist at least giving the idea. So the idea is what? If this set is dependent, that means there's a non-zero solution to the linear combination, which means you can solve for one vector as a linear combination of the others. Okay, you can do that in S1, and all the vectors in S1 are in S2. You can still do that. You can still solve whatever vector you can solve as a linear combination of the others in S1 would still be happening in S2. Why? Because all those vectors are still there because this is a subset of that. That's quick. That's the heart of the idea. But still write it out, make it a formal proof. Let me flip the page. There's a corollary here too, but I think I'd rather get the theorem 1.7. Again, I'm not going to spend too much time on it. I just want you to know that these theorems hold. Theorem 1.7 on the next page, it's page 40. The book says the following: let S be a linearly independent subset of a vector space V. So S, suppose S this time is again a subset of V. V is again a vector space, so the same assumptions about these. And this time though, S is linearly independent. Suppose S is a subset of this and S is linearly independent, which is different than what we were assuming in the previous theorem. We were assuming that S1 was linearly dependent. This time we're assuming that S is linearly independent. So it's sort of these are sort of bookend kind of theorems. They sort of complement each other. Then what's the conclusion? Suppose S is a linearly independent subset of the vector space, and suppose little v is not in S. So also assume that you got a vector little v, which is not an element of S. So it's a vector. Little v is an element of V, but it's not an S. Okay, so that's the assumptions. The conclusion is what? Then, if you make a new set, if you take S and union it with this other vector V, so in terms of, this was not in S to begin with. So whatever was in S, you just add the vector V to that collection. So that's making a bigger set. Then what can you say about this new space? This thing is linearly dependent. So this set is linearly dependent if and only if and only if V is in the span of S. Okay, what does that mean? Well, remember what the span, you'd have to, let me pretend I know what's in S. So for example, let's explain this. For example, if S had just 3 vectors in it, U1, U2, U3, then what does it mean for V to be in here? It means that V is equal to a linear combination of these guys. Eyes might be in the field, or if the field is the wheels, that would be fine. So this is saying that if you know S is linearly independent, which really intuitively means what? You can't get one of the vectors from the others. And then you add to that collection this new vector. The new space is linearly dependent if and only if the new vector can be written in terms of the previous ones. That makes it sound pretty reasonable, right? Let me see, do they actually prove this? They do prove it. I don't want to take the time to do it. So I'll have you read it. So read it, read the proof, it's there. But I hope it's somewhat reasonable again. Why would it be reasonable? These vectors in S cannot be created from each other because they're linearly independent. If you add a new vector to this collection and the new collection is dependent, the dependency has to be between the new vector and the old ones that were there already. That's what this is saying. Why? Because there is no relationship, there's no way to get any of the old vectors from that collection. You can't use vectors in here to, for example, solve for U3 in terms of a linear combination of these. Why? Because you're assuming that S is linearly independent, so you won't be able to do that. So if by introducing this vector, what you really done is introduced a vector that can be made up from the vectors that were there earlier. That's what this is saying. Read the proof. Let me turn the page. Before turning the page, what were the homework? Did I give you some homework on this section? What was it? I think we went through one, but I'm not positive. So remind me what the homework was on section 1.5. Crickets. Okay, let's back up. Did I give you any homework in section 1.5? From the last time?
There was nothing from the homework problems in 1.5, but you gave us to verify that there's no solution based off as an example we started in class.
Okay. We really didn't do anything in the problem, in the exercises, is that right? I think I got further in the other class. Yeah, in fact, I know I did because I didn't have to go to that meeting afterwards. So let me just give you some homework in section 1.5. True, false. They're not always my favorite, but it's okay. Do number 2. ABC. E and F. Throw an I. Number 3. Four. Some of these are quick. Okay. All right, so that's good enough. If I have time, I'll be happy to do some of these right after class. So if you're not sure how to do any of them, I'll be happy to talk about them. Almost wondering if I should throw one more in there. Let's do 9. Anything that has a dagger, I'm probably going to put in because it means we need it for something later. Okay. Next section. Next section defines what a basis is. So let's at least get that far. This is probably one of the more fundamental notions of the vector space. So we're into section 1.6. And there's a first thing that greets us is a definition of a basis. So let's put that down. Definition. A basis beta for a vector space V. A basis beta for a vector space V is a linearly independent subset of a V is a linearly independent subset of V. There's more that generates V. Okay, so generates another word for scans. So let me see if they. Okay, then they give you some terminology. If beta is the basis for V, so I'll write that down too, just so we get used to the terminology. If beta is a basis for V, we also say that the vectors of V form of beta form a basis for V. We also say the vectors beta form a basis for V or of V. So the key word here is basis. So example, in R2, beta equaling the vector 1, 0, and vector 0, 1. So that's certainly a subset of all of R2. All the vectors in R2 are all the 2 tuples like that. And so that's a subset. And it has to have 2 things to be a basis. So basis beta, of course, is the Greek letter, the second letter of the Greek alphabet for B. So beta is for basis here. And it's got to have two properties. It's got to be linearly independent. I'll circle that. And it has to generate V. It has to do those two of those things. So what does it mean to be linearly independent? We just did that. It means, let's verify this is a basis. So verify this beta is a basis. And two. Okay, we first have to verify that it's linearly independent. So if we had A1 times 1, 0 plus A2 times 0, 1, and we set that linear combination equal to 0, 0, is the only solution to this equation A1 and A2 equals 0. Well, yeah, because the first component would be A1 times 1, which is 1, and would be A2 times 0, which is 0, and that would have to be equal to 0. First component here. On the second component, A1 times 0 is 0, but A2 times 1 is 1, so that would tell you that A2 also would have to be equal to 0. And we're done with the linearly independent. So these two vectors are linearly independent, as explained in the section we just came from, section 1.5. So this is true. Now, what's the second part that we have to verify? These two vectors generate V. What does that mean? That means if you were to take any combination of these linear combination, you can get any vector you want. So what do the vectors in R2 look like? So any vector in R2 looks like, let's write it as x comma y. Well, maybe not, because x and y we usually use for vectors. So let's write it as what? How about b1, b2? Put b1 and b2 are what numbers on the real line. So now we're asking, does some scalar times the first vector plus some other scalar times the second vector in beta give you back any vector at all? This is the scan of beta, or these are the vectors that beta generates. So if you take a linear combination of the two vectors in beta, these are the vectors in V that it generates. And the question is, can you get, so in a sense, linearly independent says, if you had 0 on the right side, the only solution is this. Now we're asking, if you got any vector on the right side, is there a solution? And the answer is sure. What would the solution be? You'd have to pick A1 to be B1, and you'd have to pick A2 to be what? B2. So any vector in R2 could be written as a linear combination of these vectors. What does that mean? That means these vectors here generate the whole vector space R2, and that's the second condition. If you have both conditions, then this set is a basis. And that's what I was trying to verify. Questions on that? A basis means that the vectors in the basis can be used as building blocks of any vector you want. That's because they generate the whole vector space. And at the same time, you need everything in the basis. You can't just get away with less because those vectors are independent of each other. So you can't create one from the other. Let's do a follow-up example. is 1, 1. And 1, 0. A basis in R2. Well, all right. So instead of doing the familiar one, this, by the way, is the familiar basis. It's in terms of the picture. One vector going this way, one vector going this way. You can see why that would generate all vectors in R2 because these are the components that we're used to using in physics and other places. But this is a little different. This is saying, suppose the two vectors look like this. Let's give this, should we call it beta again? Well, let's call it beta 1. So it doesn't get mixed up with what we call beta up here. Is beta 1 a basis? So what do you have to check? Two things. You have to check that the set is linearly independent. So if you had A1 times 1, 1, and you added it to A2 times 1, 0, and you wanted that to be the 0 vector, which in R2 looks like that, does it mean for sure that both of the A's are 0? Well, let's check it out. The first component here would be A1 plus A2. So those two would have to sum to 0. And the second component, A1 times 1, would be A. And then A2 times 0 is 0. That would have to be equal to the second component here, which implies that A1 has to be 0. But if A1 has to be 0, then you can go back over here, and this implies that A2 is 0. So, question, are these vectors linearly independent? Yes. The vectors in beta 1 are linearly independent by what we just talked about in the previous section. Does everyone track that? I hope so, because I'm testing whether I take a linear combination instead of equal to 0. Does that mean the only solution is A1 and A2 being 0? And yeah, it was. Because these two equations, the only solution of both of them would be these. So they are linearly independent. Are we done? No. Well, if we were asked only to show that they were independent, yes, we'd be done. But we're asked, is this a basis? So what do we have to ask now? If you wanted to take some combination of the first vector in beta 1 and add it to some scalar multiple of the second vector, can you get any vector? Let's call it any vector B1 and B2. So B1 and B2 or what on the real line. So this is asking, do the vectors in beta 1 generate all of R2? Well, it's not obvious. Is this possible for any B1, B2? But if it were, what would it mean? It would mean that A1 plus A2 would have to be equal to B1 because the sum of the two components here would have to equal the first component here. And in a similar way, the second component, which would be A1 times 1, which is just A1, plus A2 times 0, which is 0, so I'll leave it off, that would have to be equal to what? B2. I'm checking now that I can get any vector in R2 by doing a linear combination of the two vectors in the beta 1 set. Well, okay, so this second equation tells us what we have to pick A1 to be. A1 would have to be equal to B2. And if A1 is B2, you can substitute that up in here. So what would it say? It's by substitution. It would say that A1, which is B2, plus A2 would have to be equal to B1, which implies what? That A2 would have to be equal to B1 minus B2. Okay, so there's a solution. The solution, you can get any vector in R2, that vector being B1, B2, by setting A1 equal to B2 and setting A2 equal to this. So that means these two vectors generate all vectors in R2. So what does it mean? This is a second basis. The first basis was the familiar one that we're, from calculus 1001. But this would also be a basis. So questions, because I'm out of time basically, but at least we've introduced the idea. So in terms of the picture, the first basis looked like this vector and this vector. In terms of the second one, it looked like this and this. And when you put it that way, you can see that any vector in all of R2 will be some combination of these. Could you give me an example of two vectors that do not form a basis in R2, having done this example? So I've got two examples of a basis. I have beta and I have beta 1. Can you give me a picture? How would the vectors look? Give me two vectors in R2 that do not form a basis.
Any two vectors on the same line?
Yes, thank you. So if you were given 1, 0 and 2, 0, and you call this beta 2, would that form a basis in R2? No. Why? Because what was just said is this is one of the vectors, one in this direction, the other one is 2 in that direction. And if you take linear combinations of these two vectors, you're just going to get vectors on that line. You're never going to be able to get this vector out of it, right? So this is not, these two vectors do not generate all of R2. By the way, are they linearly independent? So I'm asking, are these two vectors linearly independent? The quick answer would be no, because you can get one of these from the other, right? If they're linearly independent, that means you can't get one by doing a linear combination of the others. If you can get one by doing a linear combination of the others, then they're linearly dependent. So this collection not only is not a basis, it fails miserably. What does that mean? The collection is not independent, nor does it generate the whole space. So it's not even close. Okay. Anything here I can give you to do? Yeah, well, certainly look at the examples. So if I had a few more minutes, I would say do the reading. Read certainly through page 43 and 44. But for your own sake, look at the examples carefully. At the examples. Why? Well, I only had time to talk about a basis in R2. So examples should be bases in different sets that are less familiar to you. Look at example 2. Well, they go to Rn. So again, if I had time, I'd just go through each of these examples. Example 3 deals with matrices. Example 4 deals with polynomials. Example 5, more polynomials. So you should go through each of those. If you want. Let's see. It's not homework for this time, but for next time, future homework would include 1 and 2. on page 55 or 54. Cool. Okay, so I'm over time, I'm done. Let me take the customary minute or half minute to get some water. And then I'm happy to come back and do any of these problems in detail or answer any questions. For those who can't come to the session right after class, after the weekend, continue to save your homework. I know it's not going the way I want on the homework, but things are going to get better in that regard. So just hold on to it at this point. I'll come back to you on Monday on the homework. Okay, I'll see you in about 20 seconds. Okay, I'm back. Never really went away. Questions on anything we did today?
I had a question on theorem 1.6.
Theorem 1.6. Yeah, this one, which, yeah, was supposed to be an exercise. Sure. What's your question?
So suppose the S2 was linearly dependent. Would that also mean S1 is linearly dependent?
Not necessarily, because, yeah, so you're asking, that's a nice question. It's actually trying to understand this theorem a little bit in terms of other possible assumptions. If S2 is linearly independent, intuitively it means you can get some of the vectors in there in terms of the other vectors in there. And you're asking me if that happens in S2, does it automatically happen in S1? And the answer is no, because maybe the vectors that are dependent in S2 don't all appear back in here because this is a smaller this is a subset of that, right? So here's a more concrete. So the answer is no, but here's a more concrete example. So suppose S1 subset of S2, which is a subset of R. Let's make it yeah, well, why not make it easy? Okay, so suppose S1 just has the vector 1, 0 in it. And suppose S2 has the vector 1, 0 and 2, 0. Okay, this set is not linearly independent. Why? You can get this vector from this one just by multiplying by 2, right? So this set is not linearly independent. They're linearly dependent. But this set is linear independent. There's only one vector in there to begin with. So it's sort of automatically in there. You're not going to have a relationship between vectors if there's only one in there to begin with, all right? So does that make sense?
Yeah,
So,
thank you.
so you're welcome. That would be an example where it doesn't work. Now, could it work? Sure, I guess you could have something like, let's see. I guess, could it be that this would be independent and this would also be dependent? Yeah, and the easy example of that would be 1, 0, 2, 0, 3, 0. That could be your S2. And this could just be 1, 0, and 2, 0, right? So here's an example of what you're asking. It could work. It could be that this set is linearly dependent. In fact, they are, because each vector is a scalar multiple of the first one. And here's a subset of it, and it's also linearly dependent. So here's an example of this is dependent and so is this. But this example shows that this doesn't happen all the time, right? So I hope that helps.
Yeah, thank you.
You're welcome. Other questions? If there weren't, if there are not other questions, I think I would look at our homework. Um, So what about the homework that I assigned either anytime in the past or today? Today's homework is this.
Can we do problem 15 in section 1.4?
Sure, we can go back. That's not a problem. 15. Let me see what it's. Let me get some. Let me get some new page. Find on that. Gotcha. You still can see this, I hope. 15 is the request, and I'm sorry, it was what, section 1.4?
Yeah, that's correct.
Yeah. Let me see what the question is. So it says that S1 and S2 be subsets of a vector space. Prove that the span of the intersection is contained in the intersection of the spans. Okay. Let me write that down. So they want to say. So you have, here's the setup. You have S1 is a subset of a vector space, and so is S2. B is a vector space. And what we want to prove is that the span of the intersection is contained, or no, not contained, equals the span of the first plus the span of the second. Okay. And okay, well, okay, it goes back to another problem. The sum of the sum of two subsets is defined in the exercises of 1.3. Well, no, I'm sorry, I'm in the wrong place. Okay, so that's what they want. Yeah, I was in the wrong spot because I was doing 14. So this one would be, I did have containment. So let me correct this. This should be contained. And this should be intersection, I think. So let me see if I finally got what we're trying to show. Prove that this is contained in that. And then there's a second part, give an example in which the span of the intersection and the span of these are equal and one in which they're not equal. Okay. So let's go through it. One is a proof. And yeah, okay, let's do it in the order they request. So let's picture what S1 and S2 might look like. So I'm not sure this will be the most rigorous proof, but I think it'll work. So let's suppose, maybe let's get the idea. Get the idea, kind of proof. So let's suppose that S1 has two vectors in it, U1 and U2. And that's this again, just to get an idea. So I'm taking a simple case that S1 just has two vectors. Now we have to decide what S2 looks like. Why don't we suppose that it has three vectors in it? Something like that. Okay. Now, since they're asking us to take the intersection of these things, if these were all different, then the intersection would be empty, and that wouldn't be particularly a common example. So let me just make it like this. Just to get the idea. Suppose S2 had U1 again and U2, but it also had U3, where these are all distinct. Okay, so if this is how S1 looks and this is how S2 looks, then we can certainly understand what the intersection would look like. The intersection would be the vectors that are in both, right? Which would just be what? U1 and U2? You would lose U3 because that's not in the intersection, it's not in both. Okay, so let's at least get the idea trying to see why this thing works in this case. So then what would be the left side of it? The left side would be the span of this would be all linear combinations of this. So what would be in here would look like A1 U1 plus what? A2 U2? Where A1 and A2 are what? Things on the numbers on the real line. Okay. So that's how things in there would look, because the intersection is this and the span represents all linear combinations of these vectors. What would this look like? Well, this would be the span of S1. So that would be, it would be things that also look like, I'll put it above here, linear combinations of this. So again, it would be A1 U1 plus A2 U2, where again, A1 and A2 are still in R. That would be something in here. And how would something in here look like? Something in here, since S2 looks like this, would look like A1 U1 plus A2 U2 plus what? A3 U3? Okay, where A1, A2, and A3 now are also real numbers. So for this simple example, let's see if everything works. Things in here look like a combination of U1 and U2. Things in here look like a combination of U1, U2, and U3. But if what I'm arguing is everything in here is also in here. Why? Because if you choose A3 to be 0, you'll get a linear combination of these two things. So what I'm suggesting is that in the intersection here, you have all linear combinations that look like A1 U1 plus A2 U2. If you add A3 U3, you know you'll be in here, but you have no guarantee that you'll be in here because these are just linear combinations of these two vectors. But I can see that A1 U1 and A2 U2 are in here for sure, and in here by taking A3 to be 0. So, and things in here look like this. So what we actually have is an example here. Well, let me make sure I've got this right. I think I have equality. Well, but it may, yeah. Yeah, if U1, U2, and U3, it depends. Okay, it's more complicated. Definitely, though, I have this inclusion in this case, because if we're a vector in here, then you have this kind of description. And if you're a vector in this space, intersection this space, that also includes everything that looks like this, because I said you can get this by just picking A3 to be 0. So every element of this is automatically also contained in here. Now the question is, does that kind of proof generalize? Let's think about it. In this case, I really did, what example am I doing here? I'm doing this. S2 is a bigger set. And S1 is a smaller set. It has only 2 elements, and this has 3. So this is sort of what I've done in this example. And in the example, I was able to show that everything in this set is also in this set. Now the question is, does this work in general? Yeah, but we'd have to start taking different possibilities here. In this case, the intersection of these 2 sets was just this. So I think what you probably have to do, not have to, but maybe, do cases. The case I just did is when S1 was a subset of S2. I think in the case that I just did, this argument will work. I think it will also work, so call that case 1. I think it will also work in the case that these are reversed. S2 is a subset of S1, because I think it's pretty much the same argument. So if one set is a subset of the other or the other way around, I think we're good. So what's the more interesting case that I haven't included? So these 2 pictures look like either this one or like this. Okay. So what's left? Well, I suppose they could look like this. They could have nothing in common. That would probably be my case 3. S1 intersection S2 is empty. And then what's left? What's left is they intersect, but they're not contained in each other. So then I think the other case left to deal with is this one. Now, could you do it without doing cases? Maybe. But I think it sort of cries out for cases, to be honest with you, because you don't know how these sets are related to each other. So let me back up. In the case that one set is a subset of the other, that's the case I did with this example. And that would be true. It doesn't have to be 2 things in here and 3 things in here. There could be 5 things in here and 10 things in here. As long as all of these are within that, the same argument will work. So I'm ready to check off these 2 are working, and I'm ready to explore the next 2. But if you don't see these 2 are working, it's a good time to ask me for more details. I'm a little curious how they do it in the back of the book, because I'm doing it in cases. So I have in the last case here, which I didn't put down, case 4, would be this kind of case. I don't know how to put that. The intersection is S1 intersection S2 is not empty, but S1 is not a subset of S2, and S2 is not a subset of S1. That would describe this situation. Why don't we do the next one? This case should be easy. If the sets have nothing in common, if they look like this, then what are we trying to prove? If they have nothing in common, then we have the span of the empty set. And the span of the empty set, what was that? think that was the empty set, wasn't it? Or was it the zero? Does anyone remember? You sort of knew back here. So let's go back and see what the span of the empty set is. So that should be in the set. Yeah, that was the answer to our true false question. The span of the empty set is the empty set on page 33. So I think and the definition has it there. The span of the empty set is up. The span of the empty set is not the empty set, it's the zero vector. That's on page 30. So the span of the empty set is the zero vector. Okay. And that would be what we have here. So we have just the zero vector. Each of these are what? Subspaces, because the span of any set is a subspace. That's a theorem, which means each of these have the zero vector. So the zero vector is the only thing in here, and it's in each of these. So the subset is true. So this case is done. Okay, so the only case left is a case that looks like this, where there's some intersection, but there's some intersection, but there's stuff in one that's not in the other, and vice versa. Okay, so let's do an example of that just to see how it might look. So maybe S1, just to get an idea. Let me make this picture and give you the idea. Here's S1, here's S2. Suppose this is U1, that's in both. U2 is in this guy, and U3 is in this guy. So that would be an example of this, and all of these are distinct, okay? So there's only 3 vectors. And this is a simple example. It could, of course, be more complicated than this, but I think they all boil down to this one. So let's check in this one what happens. In this case, what is the thing we're trying to prove? We're trying to prove this inclusion. So what would be the span of this and this? The only thing in there is U1, and the span of it would be things that look like what? So the span in this example, I'm trying to see how the example works, would just be some scalar multiple of U1. That's what's in here, because there's only a single vector. And when you take all linear combinations, you'll just get a constant times that vector. Okay, now what do the other 2 things look like? The span of S1. The span of S1 would be all linear combinations of these things. So that would look like things that look like A1, U1 plus A2, U2. Where A1 and A2 are all real numbers or in the field. But anyway, that's what the span of the set is. There's only, in S1, there's only 2 elements, so it would be a linear combination like this. What would the span of S2 look like? It would look like something times A1 again, plus something times, let's say, U3. So this is how the picture looks. This is how the 3 sets look. And now what are we trying to show? We're trying to show that anything in here is in both here and here. But that's pretty clear, because anything in here can be achieved from this one just by picking A2 to be 0. And then you have A1, A2. And anything in here you can recover this by picking A3 to be 0. So it looks pretty clear in this example that anything in this guy will also be in both of these. And that means they're in the intersection. Okay, so that's the idea. Is it okay, if you don't know how to do something, is it okay to argue from cases that you do understand? Sure. And now you can just expand this and just say, well, first, before I expand it and tell you why it's true in general, is it clear what I'm saying here? I'm saying if this is the picture, then this inequality holds, this inclusion holds, because these things look like linear multiples of U1 only. Yes. And here they look like linear multiples of U1, U2, and U1, U3. And you can get things like this by picking the A's, A here's A2 and A3 to be 0. Okay, so now, how would this change if there were more things in here? It wouldn't change very much. If the picture looks like this, and suppose there are a couple things in here, like a U1 and a U2, I won't make it too wild. And suppose there's a U3 and a U4 here, and a U5 and a U6 here, doesn't matter. Okay, what would be in the intersection? The intersection would be linear combinations of these guys, so it would be A1, U1 plus A2, U2, that stuff. That's the span of the intersection. What would be in this, and call this S1 and call this S2, what would be things in the span here? Well, in the span of this one, it would be A1, U1 plus A2, U2 plus A3, U3 plus A4, U4. That's the span of those guys. That's what's in S1. That's what's in the span of S1. So the span of S1 looks like things that look like this. What would be in the span of S2? A1, U1 plus A2, U2 plus what? A5, U5 plus A6, U6. So this would comprise the span of S2. This is the span of the intersection. And what you're trying to show is that everything in here is in this one and in this one. But it's again pretty clear because this A1, U1, A2, U2 is right there. And if you just pick these 0, to pick these A3 and A4 to be 0, that would get you that everything, all of these guys are in a span of S1. Similarly, all of these guys are in the span of S2. Just pick A5, A6 to be 0 and you recover it. So what I'm arguing is the original argument that I gave for this works for this and works for anything in general. Does that make some sense?
Yes.
I'm curious, did they prove this in the back? I'm sort of guessing no, because you probably would have asked if they did, but let me just check. This is what, 1, 4. We're not done with it. There's a second part, I realized, but it was 1, 4, and 15, right? Yeah. So let me just see what they say in the back. Because they probably, if they prove it at all, they probably convince it real small. So I just want to put it in 1, 4. Well, 15 is not too found. Okay, so there's nothing in the back. Okay, so that's, then if there's nothing in the back, then I hope this argument makes sense. One could ask, well, you sort of did it for different cases of this. You have to, when you write up your proof, do you have to do it more generally? Technically, yes, but I'm hoping you agree that the ideas would work the same way. I mean, I could have an infinite number of things in all of these sections of the Venn diagram, and it would still work the same way because the linear combinations of what's in the intersection would be included among the linear combinations of what's in S1 and S2. That's the heart of the idea. All right, now what's the second part of the question? Second part of the question is, give an example where the span of S1 intersection X, where they're equal and where they are unequal. Well, I think the unequal would be pretty easy. So let's use our Venn diagram to get the unequal. Here's S1. Here's S2. Suppose in here, let's play off the last one. U1 and U2 are in here. And actually, let me see. What am I trying to get? I'm trying to get when this thing is bigger. So let me see. I think I should stick with the easier ones. So the easier one, this one, yeah. So suppose suppose S1 just had the vector 1, 0. Suppose we're in R2. And suppose S2 had the vector 2, 0. Okay. So when you do S1 intersection S2, you get the empty set because these are different. I mean, one is a scalar multiple of the other, but they're different vectors. So if you took the intersection of these two, you'd get the empty set. So in that case, the span of the empty set is just the 0 vector. And what would you get when you take the span of each of these? You'll get the same thing, right? The span of this will just be anything that looks like A0. Yeah, call it A0. And the span of this will also be A0. So the span of, go back up to here, this would be the empty set because the set S1 and S2 don't have anything in common. The span of the empty set is just the 0 vector. And these would both be vectors that look like A0. So you get so here's the picture. The picture is this. Pick that to be U1. That's just 1, 0. Pick this to be U2, which is 2, 0. If you take the span of either one of these, you'll get the whole line that looks like AB. When you intersect that, you get that line for each of these. And then on the other side, when you take the intersection, you just get the 0 vector. So that would be an example. That would be an example where this is not equal to that. Because on this side, you just get the 0 vector, and on this side, you get the one-dimensional x-axis line. Okay, so that's an example where what's on the left is less than what's on the right. It's a proper subspace. And an example of when they're equal, I think that's easier. I mean, if S1 and S2 are the same set, yeah, so suppose These are simple examples, but suppose S1 just had 1 0 in it. And suppose S2 had 1 0 in it. So in that case, that's S1 and that's S2. Okay, the intersection is also the same. So since all the sets in their intersection are the same, the spans of each of them will be the same. And you're just going to get equality. So that would be the second part of the question. Any question on 15? Okay. Someone have a different request? Moving on. I was going to suggest one of the new ones, but I mean, I'm happy to go back and do problems like, you know, from the earlier sections too. So whatever your interest. What's sort of clear from the way I did this problem? Look at examples. I mean, the whole thing was sort of predicated on sort of what if this looks like this, what if that looks like that, and then see if the examples can generalize. Let me go back to the previous page, maybe do one from our new homework. Maybe. Yeah, what about all these? Why don't you pick either something from 2 or 3? Well, I'd say pick something from anything you want, anything you want from this thing, but probably the earlier problems could be best. Why don't we look at 2? I could do the true false, but sometimes they cover cases that are of limited interest. So this is 1, 5. Let's look at maybe 2. Why not 2A? Start simple. Okay. They give you a warning. They give you a footnote. They say the computations in 2G, HIJ are tedious unless technology is used. They give you one of those. GHIJ. H. I did include I. Okay, so be warned about I. I guess I is tedious. Well, let's not start with the tedious one. Let's start with A, 2A. So what is it asking? Maybe there's room here to do it on the same slide. To A. It says, determine whether the following sets are linearly dependent or linearly independent. And it gives you, just has 2 objects in there. The first one is the matrix 1, -3 as the first row. And -2 and 4. And then the second element or vector, -2, -6, -2, +6, sorry. Keep an eye on me in case I'm dropping minus here. 4, -8. And OneNote dropped something on me, -2, okay. So what are we checking? We're checking whether they are linearly independent or dependent. So what are we looking at? There's only two things in here. So we can do A1 times the first one, 1 minus 3 minus 2, 4, plus A2 times the second guy, vector. These are vectors, even though they look like matrices. And when we're doing whether they're linearly independent or not, we set it equal to the 0. What's the 0 vector in 2 by 2 matrices? That would have zeros everywhere, right? So the question, this is where you start. You take a linear combination of what's in there with coefficients A1, A2. You could think of A1, A2 as being an R. And now what? Is the only solution of this? Certainly 0, 0 is the solution, right? But is that the only solution? If there's a non-zero, A1, A2, but not both the 0 solution, then the vectors are, then the set is linearly dependent. If the only solution is the 0, 0 solution, then they're independent. Okay, so how do you do it? These are sort of the components of the vector. So when you add these two vectors together, it would be A1 times this. A1 times 1 is just A1. And then it would be minus 2A2. And when you add those two together, you have to have the component over here, which is 0. And so that's the first, and now there's 3 more to do. Minus 3A1 plus 6A2 would have to be equal to the 0 vector over here. Does everyone see what I'm doing? I'm looking at the components of these vectors. Minus 2A1 plus 4A2 would have to be equal to this. And then last, 4A1. Is that right? Yes. Minus 8A2 would have to be equal to that. Okay. So we have 4 equations in each equation has 2 unknowns. And again, we know one solution of this would be all A's being 0, but is there another solution to this? And I think our usual techniques would be what we want to be used, which is, adding and subtracting multiples of equations to each other. Though, let me just look at this for a second. I mean, the first equation and the last equation are really the same. Because if you multiply this by 4 and this by 4, you get this one. So I don't think I need this equation at all, because it's really the same as this one. Now, what about the other equations? If I multiply this by 2 minus 2, then I get this one, right?
Yeah.
I think that's right. Minus 2 times this. Yeah. So that equation and this equation are really the same also. So now I've got it down to something that's simpler. Now, are these equations the same? If I multiply the top by, I could have gone through, the reduction of multiples of this times this and all that stuff, but I'm just happening to notice that these equations look similar. If I multiply this by minus 3, yeah, I get this one as well. So there's only one equation, it's this. And this one just says that A1 could be equal to 2A2. There are many solutions like that. So if I pick A1 to be 1, well, I pick A1 to be 2, then what would A2 be? 1? Okay, so it looks to me that if I pick this to be 2, and I pick this to be 1, that would give me another solution of this. Let's check. 2 times 1 is 2, minus 2, that's 0. minus 6 plus 6, still 0. Minus 4 plus 4, 0. 8 minus 8, 0. Yeah, okay, so this is a solution. So what's the result? It's linearly dependent. Why? Because this solution is not the 0, 0 solution, right? If there's a solution of this system, which is not the 0, 0 solution, then the matrices or vectors in this case are dependent. So the set is linearly dependent. Now, I just happen to notice that all these equations are the same as the first one. And if you have one equations and two unknowns, then if you can set one of them equal to something and the other will be something else, and those numbers will solve it. Questions on 2A? Is that all they wanted? I think it is. Let me get the book up again. But we're in 1.5. And we just did 2A, determine whether they're dependent or independent, and they are dependent. I think I'll leave you B, because I think it can be done in a similar way. You want to do C? Why not? Let's look at C. So maybe I'll get a new page because I think I'm pressing my luck here. Come on. No lines? No lines. Let me try again. Can't even see. Are there lines? Hey, I finally got it. Okay. So let's look at 2C. 2C, you're given this. And it has 1, 2, 3 polynomials. The first one is x to the third plus 2x squared. X to the third plus 2x squared. That's it. Okay, and then the next one is minus x squared plus 3x plus 1. Minus x squared. Was it plus 3x? But I think it could be minus 3x. No, I have it right, plus 1. Okay, so that's the second polynomial we're given. And then x cubed minus x squared. X cubed minus x squared plus 2x, and then it's plus or minus 1. I forgot what it is. Minus 1. Keep me honest, make sure I'm not messing up these as I write them out. So I have a set of 3 polynomials. 2 of them are third degree polynomials. And one of them is a quadratic. I'm just checking to make sure I didn't mess them up. I think it's okay. So we are in P3R, which means P for polynomials, third degree with real coefficients. That's where we're in. So we're looking at things that look like x to the cubed plus b x squared plus c x plus d, or a, b, c, d are real numbers. So that's how things in here look. Okay. Now, what is the 0 polynomial? The 0 polynomial is this guy, 0x to the third plus 0x squared plus 0x plus 0. That's the 0 polynomial. I hate to call it 0 again, but anyway. I'll put a vector. That's the 0 vector here. Okay, what are we checking? We're checking whether if you take the first polynomial, multiply it by a1, and then take the second polynomial and multiply it by a2, and then add it to the third the third polynomial multiplied by A3. Is that equal to the zero polynomial? Well, it is equal to the zero polynomial. We set it equal to that. And the question is, one solution for sure would be 0, 0, 0. That would give us this. If that's the only solution, then these polynomials are linearly independent. If there's a solution of A1, A2, and A3 where they're not all 0, then they're linearly dependent. Let me see. I might be able to do this. Well, okay, let me not be. I was trying to do it more quickly, but let me do it more in the standard manner. So the standard manner would be look at the components on both sides and get equations. So the component of x to the third here is A1. And there is no component of x to the third here because there is a 0 x to the third if you like. So that would be just 0. Or there is none here. And then this would be plus A3. And then that would have to equal the component over here, which is 0. So that would be one equation that would have to hold. If I look at the second degree parts of these things, it would be 2A1 from here. And then it would be minus A2 from here. And then it would be minus what? A3. And that would have to be the power on x squared, which would be 0. And then the third equation would be there'd be 4 equations altogether. There would be the power of x to the first, which would be 0 from this one. And then x to the first would be 3A2. And x to the first here would be 2A3, right? And that would equal to 0. Let me make sure I did that right. And am I looking for x to the first powers? There's none in the first polynomial. 3A2 in the second. 2A3 in the third. That looks fine. And that's that. And then the constants. There's no constant here at all. There's a constant here, so you get A2. There's a constant here, which would be minus A3. And that would have to equal 0, right? So if I've done this properly, it looks like those are my 4 equations. Does everyone see what I'm doing?
Yeah.
Okay. Well, the last one attracts me first because it tells me that A2 and A3 have to be the same. And then putting that together with the first one, I know that A3 is also equal to minus A1, right? Like I just swing this to the other side, swing this to the other side. So A3 would be minus A1. So there's this relationship here. So looking at that, why don't we just pick A2 to be 1, and A3 to be 1, and A1 to be what, -1? If I do that, all of these equations, all of these conditions seem to be true. So this is suggested since A1 and A2 have to be equal to each other by this equation, and this is suggested because A3 is minus A1 by the first equation. So I just looked at these 2 equations. And I'm getting a candidate, a non-zero candidate that I think might solve all the equations. Well, certainly they'll solve these 2. Well, let's solve this one. I don't know. 3 times A2. So A2 is 1 plus 2 times A3. That won't work, will it? Okay, so maybe I was trying to do it too quickly. Let me make sure. 3 times this would be 3 plus 2 times that. That won't work. So let's back up. Okay, so I'm trying to see if there's a non-zero solution here. So let me just, I guess, go through the usual approach. The usual approach would be to try to get everything in terms of A1 here. So I would guess I would take this first equation, A1 plus A3 equals 0. And then I would take minus twice this equation and, or yeah, minus twice that equation and add it to this. So when I do that, this will give me 0 times A1. That'll get me a 0 basically. And what am I doing? I'm doing 2, well, there is no A2 here, so this just stays the same. But minus 2 times this, and then add it to this, right? That would be minus 3. 3 equals 0. Make sure I did that right. So I'm multiplying this equation by 2 and subtracting. So that gives me 0 here. Multiplying this by 2, there's nothing there to subtract this, but yeah, this looks fine. And so far we have this. And there's already a 0 down here as well. So I'm just using the standard approach that we've been using now. I was hoping to spot something that worked, but it didn't seem to work. So I'm just trying to reduce the system to another system. Okay, and we got all zeros here. So what's the next thing to do? Probably take the A2 and use that to modify some of the other equations. So I would write this thing maybe in this order. A1, 0, A3, 0. And if I put this one as the second equation, this would be A2 minus A3 equals 0. And then this equation would just be 0 minus A2 minus 3A3 equals 0. And the other equation would be 0, 3A2 plus 2A3 equals 0. Make sure I didn't mess it up by flipping it around. I tried to put this one as the second equation. I think I succeeded in that. The one that was second is now third. The one that was third is now fourth. Everything's fine. And in order to get it to be simplified, what would we do? I guess we would add the second equation to the third. Leave the first one as it is. I'll leave the second one as it is. Add the second equation to the third. That will give me a 0 here. This to this will give me a minus 4A3. And then what? Maybe take 3 times this and subtract it from here. So that would give me a 0 here. 3 times this and subtract it will give me a 0 here. 3 times this and subtract will give me what? 5A3. Okay, so I've introduced more and more zeros. And what now? Well, what now looks, I can keep going, but it looks still from this A3, these imply A3 is 0, right? And if I know A3 is 0, that implies from this one that A2 is 0. And if A3 is 0, that implies what from the first one? That A1 is 0. So the only solution of this is the 0, 0, 0 solution, because the solution to this system is equivalent to the solution of this system, and this is it. So what does that mean? These are linearly independent. So these equations, these three, form a linearly independent set. Meaning what? You can't get one from any of the others, by taking linear combinations. Now, I was trying to do it quickly, but I was hoping that they were linearly dependent, and it wasn't working out. So then I went back to trying to solve the system, and this was forced on me. Questions on this one? Okay. So we've done a couple from this. Let me see what else there was there to do. Go back. Oh, goodness. I'm trying to get back to my homework. Yes, here's the homework. So we did a couple from 2. Should we do one of these? Anyone have a request? 3, 4, 5, 3, 4, 5, 9. Take a few seconds, look them over, see if any of them interest you. I'll do the same. So we're in 1, 5. Just did a couple from 2. Oh, okay. 3 is rather explicit. They say it's linearly dependent. So that means what? One of these matrices in 3 can be written as a linear combination of the others. You can do that. Let me think what else we have. 4. I think 4 is sort of routine. 5, sort of the same. It's 9. How about 9? Let's do 9. Unless somebody has the choice. If someone would rather do something, let me know. Probably be our last one. I gotta get ready for the other class. Let's look at 9. So get out of this page. Go to the end. Page. Let's put lines on it. And we're looking at number 9. Again, 1.5. Okay. So 9 is a dagger, so it means we're going to use it in the future. Let U and V be distinct vectors in a vector space. So we assume U and V are distinct vectors in capital V, that's a vector space. Distinct means what? U does not equal V. Not the same vector. That's what distinct means. Okay. Now what? Show that the set is linearly independent. So it's a proof. show that the set UV is linearly dependent. If and only if U or V is a multiple of the other. If and only if U or V is a multiple of the other. What does that mean? It means either U equals some scalar times V, or what? V equals some scalar times U. V could be just real numbers, for example. If you think of it. So that's what we're trying to show, that if they're linearly independent, then one is just a multiple of the other. Okay. I think if and only if means there's two directions to prove. Why don't we prove that? Well, this is the easier one. Okay, so I think it's actually easier to assume that one is a multiple of the other and show that it's linear independent. So let's show that way first. So suppose two parts, part one. Suppose U is equal to AV, or V equals VU. And then show they're independent. Show the set UV is linearly dependent. So that's going that direction. Well, okay. If U equals, oh, yeah, think about that a second. Okay, let's see how far we can go. If U equals AV for a real number, say, then U minus AV would be equal to the zero vector. Okay, and well, let's be careful. Let's assume that A is in R, but A is not zero. And this is the zero real number. Okay. So I'm assuming that U is a multiple of V, but the multiple here is not zero. So if it's not zero, then what do we have? We have a linear combination of these two guys, and there's a solution. So what's a linear combination of these two guys? Something that looks like alpha times U plus beta times V, where alpha and beta are real numbers. And they would be linearly independent if there's a solution of this which is non-zero, right? In other words, where alpha and beta are not both zero. But I already assumed that A here is non-zero. So the alpha here can be 1 times that, minus alpha times this. And okay, so this equation implies that this equation holds where alpha is 1 and where beta is minus A. And since alpha is 1, there's a non-zero solution of this linear combination. So that already implies that the set U and V are what? Is linearly dependent. Okay. And by the way, I assume that A wasn't zero, but even if A is zero, this would still work. You'd have 1 times U minus 0 times V equals 0. And one of the coefficients would be non-zero. So I don't even need to assume this. I think I'll strike it.